Welcome to our channel Creative Minds. Students, in this lecture we are going to discuss another topic of quantum mechanics, which is the topic of simple harmonic oscillator. Students, we know that a vibration of a diatomic molecule can be described by a harmonic oscillator, and harmonic oscillator obeys Hooke's law. Consider a mass m which is connected to a wall by a spring. If the force acting upon the mass is directly proportional to the displacement of the spring from the undistorted length, then the force law is called Hooke's law. Suppose that no gravitational force is acting upon the mass m, then the only force that is acting on the mass m is due to the spring. If we let L0 be the equilibrium or undistorted length of the spring, then the distorting force must be some function of displacement of the spring from its equilibrium length. Then this displacement of the spring denoted as x equals to L minus L0, where L is the length of the spring. The simplest assumption we can make about the force on the mass m as a function of the displacement is that the force is directly proportional to the displacement, and we can write it as F is equal to minus K L minus L naught, or simply F is equals to minus Kx. Here negative sign indicates that the force points to the right. If spring is compressed where L is very much less than L naught, then the spring will points to the left, and if it is stretched, then L is very much greater than L naught, and it would point towards right. And the Newton's equation with the Hooke's law is written as m d square L by dt square equals to minus K L minus L naught. Here K is a proportionality constant, which is also called as spring constant, and a small value of K implies a weak spring or loose spring, and large value of K implies a stiff spring. So if we let x equals to L minus L naught, then this equation d square L by dt square can be written as d square x by dt square. Here L naught is again the constant, which is the equilibrium, the length of the spring at equilibrium position. So this equation can be rewritten in the form as m d square x by dt square plus kx equals to 0. Students, the general solution to this equation is xt equals to c1 sin omega t plus c2 cos omega t. And we know that omega is equal to square root of k by m. Suppose we stretch the spring so that its displacement is a and let go, then the initial velocity in this case is 0. So from the equation, it would become x of 0 is equal to c2 is equal to a. By putting the initial velocity 0, and then dx by dt at time t is equals to 0 is equal to c1 omega. These two equations imply that c1 is equal to 0 and c2 is equal to a in general equation. Thus the general equation would become xt is equal to a cos omega t. Student, the displacement versus time is plotted in this figure, which shows that the mass oscillates between back and forth between a and minus a with the frequency omega radians per second, or frequency equals to omega by 2 pi cycles per second. The quantity a is called here the amplitude of the vibration. This is an illustration of the displacement of a harmonic oscillator versus time. Students, now we are going to discuss the energy of harmonic oscillator. Let's look at the total energy of the harmonic oscillator. The force is given by the equation as the derivative of potential energy f of x equals to minus dv by dx. So that potential energy is Vx is equal to minus integral f of x d of x plus constant. Using the equation, as we have already discussed, that the restoring force F is equal to minus K L minus L naught is equal to minus K of x. By putting it in this equation, this potential energy become Vx equals to K by 2 x square plus constant. The constant term here is arbitrary constant, and that it can be used to fix the zero of the energy. If we choose the potential energy of the system to be 0 when the spring is undistorted at x is equal to 0, then we can write potential energy as k by 2 x square. This is the potential energy associated with the simple harmonic oscillator. The kinetic energy is given as T is equal to 1 by 2 m ds by dt whole square, or 1 by 2 m dx by dt whole square. Using the equation xt equals to a cos omega t, for xt we can rewrite the kinetic energy term as 1 by 2 m omega square a square sin square omega t, and potential energy as V equals to 1 by 2 k a square cos square omega t. Students, both T and V are plotted in this figure, and the total energy of the harmonic oscillator, which is the sum of kinetic energy and potential energy, is given as 1 by 2 m omega square a square sin square omega t plus 1 by 2 k a square cos square omega t. And if we recall that omega is equals to square root of k by m, we see that the coefficient of first term is k a square by 2, and thus the total energy would become E is equal to k a square by 2 sin square omega t plus cos square omega t. And we know that sin square omega t and plus cos square omega t is equal to 1. So the total energy E would become k a square by 2. In this figure, the kinetic energy curve is labeled as Tx, and the potential energy curve is labeled as Vx of the harmonic oscillator during one oscillation. The spring is fully compressed at minus A and fully stretched at plus A, and the equilibrium length is at x is equal to 0. The total energy is horizontal, and this is horizontal curve and is labeled as E equals to sum of kinetic energy and potential energy. Students, from this lecture we can conclude that the total energy of harmonic oscillator is constant and is equal to potential energy at its largest displacement, where kinetic energy is 0. And this figure shows that the how total energy is distributed between potential energy and kinetic energy. Each oscillation between plus A and minus A such a way that the total energy is always constant. So we can say that the total energy is conserved and the system is conservative system.